give a very short kind of preamble to the whole thing. Then after that, we'll give about 5 minutes, okay, maybe 4 minutes to be precise, to each of the panelists, okay, for their general description of what they think about this particular panel. And after that, we'll open it to the audience so that there can be interaction, and we can continue overall for about 1 hour or so, okay? So this is quite an interesting topic. It's called EEX, okay? Now, this means what is going to happen in future, okay, the future of EE, electrical engineering as such. And if you are an agnostic, if you don't like such kind of predictions of future, you may say it's X, kind of with a, your different way of saying it will explain what you mean by X or X, okay? Now, personally, I feel that the whole concept of electrical engineering, of course, there are other areas also. There has been rapid growth in last 20, 30 years, okay? And certain things are really exponential, okay? You might have heard terms like Moore's law and others, okay? And in certain cases, the progress has been so rapid that it's, forget about the students even catching up with what's happening. Even for us, we have been doing, teaching and doing research. Even for us, sometimes it's extremely difficult. Okay, even in electrical engineering now, I know only very small part of it because it's a very vast area. Okay, and there's so much of development. So we need at least 5 of our people to represent one department, okay, electrical engineering. That shows the vastness of them and how actually it has grown. Of course, today what you see there, what you're going to see in 5 years down the lane is going to be probably a lot more different, okay? Let's say start with miniaturization if you look at it, okay? Whatever was there, like when I started doing my PhD, okay, or not PhD, even at the graduate level, the first thing, okay, we had to actually get into we did not have CRT, right? So we had to actually, just the time the CRT was coming in, so it was, if you could punch, the punching card if you have seen, that's where you have to feed it to the computer. And if you can, let's say, type 10 lines correctly, then you have achieved a great thing in that, in that particular day. Whereas today, one day you can write a lot of codes, you can get things done, things are faster. When I came back from US to study, to join here, I brought a computer, and then, what was the clock speed for the computer? It was like something like 8 megahertz or something. And what is the clock rate today on the computer? Right? Anybody? Any guess? 2.4 gigahertz or megahertz? Gigahertz. Okay. So see, that is almost like 1,000 times, right? It has gone up in only last 25 years. Similarly, if you look at the data storage, okay, now you compact everything. Now you can capture audio, video, you can send it, you can do everything instantaneous. Okay, I think it is a good thing, bad thing, because yesterday I found that in higher secondary exam, I think there was some paper leak in, I think, Marathi paper. And in our time also, I was telling that we had paper leak, but we could never figure out, who leaked and who all benefited. But today, in 10 minutes, probably the entire country you will have a copy of that, right? That's the power of technology, and all this electrical engineering has been part of it, okay? So, of course, I have not said anything about our, it's not only in informatics and microelectronics. There has been significant development even in control and computing, because if you read the newspaper, I think 2 days ago, our new friend in the block, Donald Trump's, one of the associates said, we are shocked that India could send 104 satellites in one go, right? So that actually shows the power of where we have taken our control and computing, apart from actually designing. So that's the kind of thing that we have gone. And if you look at our the electronic, basically the power electronics and power this one. See, earlier days when you could actually, today you can select like mobile phone, whether it's an Airtel or Jio or whatever. Now you can even select whether I want Tata or Reliance and others. Can you imagine that some 20 years ago or something, that I can select whichever way that today I prefer this particular electricity supplier, right? So all these things are possible thanks to the wonderful development in electrical engineering, but that I can say that because we are now in today. But this panel is about what's going to happen after this, what all we can think of, okay? So let's start with the panelists. Maybe who wants to volunteer first?
Youngest one.
Youngest one first. Okay, so let's hear what's going to happen in each of their area of specialization, and then we'll throw it open. Okay, please sit down.
Hey, welcome again, everyone. So maybe I think the way I'll do this, I'll use my 4 minutes is I'll tell you about what I do. So that will give you sort of an idea of what questions to throw my way, and my understanding of where I think electrical engineering is going. So my basic research area happens to be in micro-electromechanical systems, so the acronym for which is MEMS. I think that's how most of you may have heard of it. So MEMS is, if you think about it, is not a conventional EE field, right? So it's a field which started in the 1980s or a little before the 1980s, but over the years it has become very much an integral part of electrical engineering. It deals with very different kind of systems compared to the rest of the topics in EE. These devices are not fundamentally electronic devices. At the very core of it, these are mechanical structures. But the way you interact with these mechanical structures, the techniques you use, they lie very much in the electrical engineering domain, right? So conventionally, the way MEMS engineers used to design their devices and all the products that have come out, these used electrical signals to interact with these devices, right? So for those of you that don't know the field of MEMS, I mean, if all of you have cell phones, the two most successful MEMS products are already in your cell phones. One is, actually there are multiple, not only two. So there's accelerometers, gyroscopes, you have MEMS filters. Every cell phone has a MEMS filter because an electronic filter cannot meet the performance that a MEMS filter does, right? So it's a very successful field, relatively new, that has grown and become very much part of electrical engineering. But these days, MEMS researchers are not working with only electrical signals. So even in MEMS systems, you have multiple different kind of physics being used. So my particular research happens to work with light. So instead of using electrical signals to interact with these structures, I use light to interact with these structures, right? So as you can imagine, very different kind of wavelengths. When you work with light, you are very, very high in frequency. So you can do a lot more things that you cannot do with RF electrical signals. Not only light, there are many different aspects that are coming in. So a recent field that has started, and even in our department, there's a lot of interest, is this field of spin mechanics. So every electron has a spin momentum, right? So you can use that spin momentum and now interact with the mechanical structure. So, I mean, for some of you and even for me, it's not very comprehensible. I don't quite understand how to use this effect. But as you can see, mechanics, if you think about a MEMS structure, it's a mechanical structure, but you can do so many things with it if you just use different kinds of physics. And as the field of electrical engineering, as our department grows, as this broad domain of engineering grows, I think all these fields are going to come in, and the concepts that you really use to work with these structures still lie in this broad area of electrical engineering. So that's my sense of where I see the field of MEMS and microsystems going. So maybe we can have a discussion about that.
Thank you. Thank you, Siddarth. Okay, so Bhaskaran has already picked up, so let's hear what's happening there in quantum areas.
Once again, thank you for giving me a chance to speak. And since my colleague told a lot about miniaturization and mechanical systems, I would go further ahead, sort of continuing a little. So the first thing is that, as Professor Subhasis Chaudhury said, there is something called Moore's law, which sort of is the catchy thing that says, you know, devices are getting shorter and shorter and things like that, right? And so, you know that today's nano device, I mean the Intel's transistor, what is the active length? It's about 22 nanometer, right? So Intel is running the 22 nanometer node. So a lot of interesting things happen And because of that, this field is progressing at such an enormous pace. Right? 30 years ago, quantum mechanics was some sort of, what's it called? Something like science fiction. You know, like quantum chalega, it is some 1920s theory, explained something, and our real devices are working in some other regime. However, as the devices got shorter and shorter, the quantum phenomena started appearing so overtly that you cannot just bypass it. Today, when I start teaching a course in nanoelectronics, I start with one slide saying, look, miniaturization, blah, blah, blah. Sizes got down from 1 millimeter to 1 nanometer. But do you know that the concept of conductance has got quantized? And this is something that makes everybody's face light up. Oh, is that true? And one of the most bizarre consequences of that is how your devices work today. So what I would like to say is that although these devices have achieved a lot of power and potential, as you can see, today's devices are small, the data storage capacity has gone super high, but the unseen hero in all this is the electron, and it is the flow of current at the nanoscale that really controls the future devices. Let me put it this way. Now, as Professor Siddarth mentioned, the electron as a package is not just the charge, but it also contains its spin and it also carries some heat energy. So tomorrow's devices would be at the nexus of engineering the charge, controlling the spin, and controlling the energy together. And there is a very hot term for this: spin mechanics, spin caloritronics. These are all very upcoming areas. And unfortunately, the field is rapidly progressing that by the time I read and understand a topic, the field has moved on and I'm like frustrated all the time. Right? So in terms of spintronics, I'll give you an example. For example, last IEDM conference, or some of you know that it is the most important conference in devices. It's called International Electron Devices Meeting. The company called Hynix announced a 4 GB chip based on a very bizarre phenomenon, for you at least, called spin transfer torque. So it is called spin transfer torque RAMs. It literally switches a device from 0 to 1 state by using a torque exerted by a spin on the other. Just like I kick that door, it opens the other side. The same way electron spins in one direction, kick the entire magnet and turn it over. So this device has now become practical. 20 years ago it was science fiction, you see. So I would just go toward the ending and say that you should not think that something is very, very advanced physics, it's very deep stuff and it's science fiction. Rather, you should imagine that future devices will start using some exceptional concepts that you will develop today in an exploratory front, right? So this field is sort of open, and it is also heading to an embarrassingly multidisciplinary field. Okay, so today we need inputs from biologists, material science engineers, and chemists, for all you know, and that is the reason why this field is sort of moving so ahead, because now it has become a truly interdisciplinary heaven. So please do not keep boundaries in your learning, is the first thing I would like to advise. And of course, the future really holds for something more advanced that include aspects such as quantum computation, quantum information, and so on and so forth. I'm expecting by 2050 that the world is seeing such bizarre things. So with that, I would like to tell you, stay open-minded and start learning and try to appreciate many things that are around you. Thank you very much.
Thank you, Prof.Bhaskaran. So we start with now on the power electronics side.
First of all, apologies for coming late. In the sense, in fact, I was well on time. Students told me, sir, there is no one there, you can come afterwards, 11:20. So I went back. I'll stand up and talk. I feel uncomfortable. My area of expertise, I work in the area of electrical machines and power electronics. It's an age-old area, maybe. But then, over the years, if you see, two things have come down. One is maybe as Prof.Subhasis said, the communication time. But the second thing that has come down, the travel time. Travel time has significantly come down. Okay? Yes, maybe today, maybe IC engines or whatever they may be using. But people are talking about today all electric aircraft, all electric ship, all electric vehicle. The other day, I heard someone saying, I would like to buy, okay, I'm asking you a question, which car you would like to buy, given a choice? If you have.
Tesla.
Huh?
Tesla.
Ferrari, oh no. Someone said Tesla. Before Ferrari, someone said Tesla. Yeah, Tesla, today Tesla has become a household name. Everyone talks about having a Tesla car. It's again an all-electric vehicle, electric car. Another thing the world is talking about is the global warming. Against that, none of us can do anything. In what way we can control global warming? People are talking about greenhouse gases. So one way to reduce the greenhouse gases, people said conserve electric energy very efficiently. So the future, at least belongs to the power electronics, power conversion area. Okay, we have to convert electric energy very efficiently. Without that, without power electronics, you will not be able to do. I said all electric vehicle, all electric aircraft, all electric ship, the constraints are going to be, or whatever the motor that you are developing, the power density has to be as high as possible. This is, you can't build a huge motor, and then you need one more vehicle to drive, carry that motor. Okay, the power density of the motor is very high. I'll just give you certain figures. Today, the conventional machine, the current density is of the order of 5 ampere per mm square. Okay? The Siemens, the other day, they talk about 20 ampere per mm square, 4 times higher. See the amount of heat that is generating. Okay? So therefore, of course, that has the heat that is generated has to be cooled. Okay? So if they have developed the motor which is having where the current density is 20 ampere per mm square, thereby increasing the power density, I do not know where the next target is going to be. Okay, so second is converting. I did not know till the other day. No one was talking about solar power generation or power conversion or power generation using non-conventional energy sources, wind and solar. By 2022, country like India said by 100 gigawatts of power we have to generate from solar PV. As of now, we are generating around 9 gigawatts. 9 gigawatts of solar power. We are generating now, by 2022, 100 gigawatts of solar power. How do we achieve this? Of course, without the progress in power electronics and this area. Of course, if you over the years, if you see, the progress in power electronics is primarily because of the microelectronics engineers. Okay? Initially, there were very slow devices. Now there are reasonably fast devices are available. People are talking about the next generation power device, which is made up of gallium nitride wide band gap devices. They seem to be blocking the voltage in both directions. Whenever there is no device today, we have a power semiconductor device which blocks AC voltage, a symmetrical device. Okay? So if that comes, it is going to revolutionize power electronics. Okay? Yeah, that and I think I'll stop here.
Next, Prof.Girish.
Yeah, I'm Girish Kumar. I work in the area of microwaves and antennas. Mainly you can say communication area. And I started with the cell phone. There was a reason. So we have 2G, 3G, 4G has already come. And now 5G is the next big thing which is going to be there very, very soon. And the expected time is 2020. So we are sitting in 2017. We are talking about data speed of 1 megabits per second or 10 megabits per second. That is all going to be history. You're going to talk about 100 megabits per second to even 1 gigabits per second. And along with the 5G, we also have something future which is IoT, Internet of Things. In fact, I recently attended one of the industry meet, and they are projecting 5G along with IoT will be a $7 trillion business. And just to tell you, India's GDP is $2 trillion. China GDP is $5 to $6 trillion. USA GDP is $13 trillion. And now we are talking about just one technology that will have a GDP or the total valuation is going to be $7 trillion. And of course, for that to make happen, a lot of innovations have to be done. So I mean, you have to really seriously think about microwaves and antennas in time to come. But along with that, you need to develop those devices. So a lot of device people have to work with that, and a lot of integration has to be done along with that. In fact, actually speaking, he mentioned about gallium nitride, but even at microwave, we use gallium nitride devices, and at gallium nitride at microwave are basically used for very wideband application as well as for high power generation. In fact, majority of the time, solid state devices actually generate very less power, maybe 10 watt or 20 watt or 50 watt. But just to tell you, if you have used microwave oven uses magnetron. Probably in the next 3 to 5 years, you will see solid state microwave oven where you will have these GAN devices or LDMOS devices and other things. So there is going to be a lot of devices application which are going to come. But before that, I also want to mention, sometimes we have to think of the future, but we have to also take care of the present. And I very strongly believe what Modi ji, our Prime Minister, says, which is make in India. Right? But however, he talks about make in India, he goes to China, he goes to Japan, he goes to USA, he goes to Germany and tell those people, come and make in India. In fact, I took an example of iPhone, I'll repeat that again. So Apple is planning to make iPhones in India. In fact, that proposal is going on for more than 1 year. But since we are desperate for them to come over here, they are demanding a lot of freebies, okay? So the reason why he is not going to Reliance and Tata to tell them to make in India. Because the most important thing is before make in India to happen, it has to be design in India. So when in our curriculum, when you do the study, in fact, I know that majority of the students don't like to go and work in the lab. But I think you have to change your thinking. Just sitting on the computer, writing the codes and just running the program is not going to make in India initiative. And why I say make in India is the greatest initiative. By make in India, you are going to create jobs for crores of people. China has already proved that by doing manufacturing, they have now become the second largest economy in the world. Look at China 40 years back, they were nothing. Okay, so manufacturing can only happen if you do design in India. Design in India will only happen when you start working on the thing. Prof.Subhasis Chaudhury talked about satellite. So in satellite launching, India launched 104 satellites. It is a great record, but it also had a lot of challenges. And I'll tell you one beautiful thing happened with the ISRO program. It's a very, very strange thing. The whole program took acceleration because Western world put sanction on India. And when they put the sanction, they could not buy or import those things. And then they were forced to develop these things in India. Okay? So in fact, ISRO is the greatest success story of that particular sanction. So remember one thing. So if you are down in the dumps, probably that is the time to learn, work hard, take the challenge, take the bull by horn, and then proceed forward. Alright, so I want that all of you should start thinking about design in India, make in India, and then we'll continue from there.
Yeah, maybe Professor Sule now.
I will also stand and speak. I think it's not so easy for me to say what is going to be most exciting or the next important thing in electrical engineering as far as this area of control and computing goes. Okay. Because historically, if you see, the first dinosaur bone was found in Utah province in US in sometime in 1850s. That time, within about 10 to 15 years, the American universities had launched this area of paleobiology. Nobody thought that time that this had any importance. Even if you go back to the observations made by Kepler, about the orbit of Mars, retrograde, everything. What was the use of Kepler's measurements? You see, today we are all talking about satellites, this, that, and viewing, say, Donald Trump's elections or football match there or whatever. That is because there are all these satellites sitting there, they are being controlled from Earth, and communication is all working perfectly, and sitting here you are able to see a video being taken somewhere else. So this has required putting those geosynchronous satellites there in perfect orbits, and that has required doing accurate calculations using Newton's laws of motions. How did Newton discover his laws? Not by looking at falling apple, but because of Kepler's observation. So astronomy had this application. So today the fruits of technology that we have are in the Kepler's hard work on trying to make measurements about the Mars. So you never know which things are connected where. You see, artificial intelligence was formulated in the way back in the 50s, early 50s. The person who actually did this was more like a radical. He was an activist. He was never accepted properly in the university system. He was an activist in the US, McCarthy, John McCarthy. But today, whatever he created has become very important. So you really can't say what will be important. Apollo program, of course, would not have succeeded unless a lot of innovation in system theory, identification, algorithms, controls. Had it not been developed, there would have been no Apollo launch possible. Okay. So there is a cross connection between various technologies as far as control goes, and all the technologies that people have talked about, whether it is photovoltaics, energy conservation, climate control, space applications, now robotics, somehow nobody mentioned, but that's one of the applications where control technology is going to be used very, very decisively. So let me come down to systems where, well, there are generally slow and fast systems. You need controls to run an aircraft smoothly, you need controls to run say a high-speed train without vibration. Otherwise, you see, it will not be possible. See, normally the buses on the highways and the roads, they take care of themselves and the vibration simply because of the advancements in technology of springs and so on. Beyond that, if you want to do it at high speed trains require active vibration control, and without that, no high-speed train can work. And so that is one area which has already become very standardized, and controls have been used there. So these are all fairly exciting areas, but even then there are two types of areas broadly where controls has been very effective. One is, of course, the slow moving things, whether it's an aircraft or a ship or controlling a turbine or whatever. As long as these are moving relatively slowly compared to the electronics, because electronics is fast, the bandwidths are in the order of kilohertz and megahertz. On the other hand, these physical devices are very, very slow. Their bandwidths are of the order of few hertz, because mechanical actuator doesn't work faster than that. But of course, mains will have bandwidths much larger than that. But even then, electronics that is used for controls is much faster than the physical system. So as long as those physical systems are slow enough, control problem is easy enough. So one has to come down to control problems of fast systems. Okay. I think one of the greatest challenges that is going to be seen in the next few years is in the area of singularity. How many of you have heard this word singularity? Can you raise hand, please? Just 1, 2, 3, 4, 5. Very small number. So I think first thing you should do is when you go back home is to go to the internet, type the word singularity and find out what's happening on singularity. Singularity is an area which has come up because of the possibilities that now the device technology, the electronics has become fast enough so that the time that takes for nerve signals from brain to, let's say, hand, this time has been matched by physical devices very closely, and in the next few years electronic devices will be able to create artificial hands and limbs and everything, in which this signal transmission from the neurons to the actual physical device will be as fast as it takes in the real biology, for example in the animals. And then there is a big plan of, so people are already looking at the consequences of this new technology. This new technology will create robots which are going to be used for imitating lots of human-like functions. Just like, for example, washing utensils is one function where you would like to replace human being by a robot. Doing all sorts of chores in the house, doing so many things which human beings do expertly and quickly, but we would like to replace them by robots. That is one area where fast controls are going to be required, and it's already a challenging problem. Second problem, as I see it, is in the area of quantum electronics or quantum electrodynamics. And control of quantum electrodynamic systems is being studied only right now at the theoretical level, but most of the areas are open. With this, actually I would like to come to another exciting area which is connected with computation, and actually I used to work in control area but stopped working in it for the last 10 years and shifted over to a new exciting area called cryptology. So I won't have much time spent on cryptology, but cryptology is concerned with very important aspect that all of us are worried about in our day-to-day life, that is security. Security of information. And there are lots of challenging problems there, lots of problems which have not been solved, and they all connect with some of the challenges in computation. And well, although this area is fairly technical, but those problems are going to actually affect our lives in terms of artificial intelligence, computational algorithms, trying to solve massive biological computational problems which will decide personalized medicine, drugs, solution to diseases like cancer and HIV and so many things, where all of these are being converted into computational problems where solutions will be found. New molecules are being generated by computation. So computation is going to take an important role as much as development of devices and new technology. And that's, I think, is one of the most exciting and important area in the next few years. Thank you.
Thank you, Professor Sule. I think before we do anything else, let's go, throw it open to the public. Let's pick up some questions from the students. Okay. So who would like to be the first volunteer? Ask any question you may want to have on electrical engineering to the panelists. What? Any Isaac Asimov or Jules Verne? Anybody here in the audience? Yeah, there. Okay, good.
I just want to ask a generic question, like.
Now, is there a mic there somewhere?
Benefit of the rest of the
here
people
and
to
ask
come.
so that
Yeah.
everybody hears the question.